This lesson starts topic 3.2, which is modeling a gas. Our objectives in this unit are to discuss and define what pressure is and the equations of state for an ideal gas. You'll understand this primarily as the ideal gas law. But what's more important in this unit is understanding the kinetic model of an ideal gas. What model are we using? And what are the assumptions based in that model? So we'll be solving problems, using the ideal gas law, which is PV equals nRT, and interpret the changes of state for an ideal gas based on pressure and volume, pressure, temperature, volume, temperature diagrams. So we have four formulas in this section. The first formula says that pressure is equal to the force applied divided by the area that force is applied on. The second area for formula here is basically Avogadro's formula that says the number of moles of a substance is equal to the amount of that substance divided by Avogadro's number, n sub a. The third equation is the ideal gas law, which says pressure times volume is equal to the number of moles n times the gas constant times temperature in Kelvin. That's the important part in this one, Kelvin. The fourth equation is Boltzmann's equation that says the average kinetic energy is proportional to temperature, and the formula is given there. First off, let's talk about pressure. Right here on the right hand side, I basically have a molecule that's moving around in a box. It's bouncing, bouncing between walls. Normally there'd be many molecules, but we're just focusing in on just this one. Since the molecule is in motion, it collides with the sides of the box. As a result, it changes direction, which means that there's an acceleration and a force or impulse on this molecule. The sides of the box exert that force on the molecule, and Newton's third law basically says that the molecule exerts an identical but opposite force on the side of the box. And it is that force, imagine lots and lots of molecules, but that force divided by the area of the wall is what we call pressure. So pressure is basically just lots and lots of molecules bouncing against a wall, or a surface. And the formula there is given as force divided by area. The SI unit that we're going to use for pressure is the Pascal, abbreviation capital PA. In the imperial system, it's pounds per square inch, or PSI. The 1 Pascal basically corresponds to 1 Newton per square meter. An unofficial unit that we'll run across kind of frequently is the atmosphere, or ATM. 1 atmosphere is roughly the air pressure at sea level, because that changes with weather and the sea level even changes. It's not an exact unit until they defined it to be exactly 101.325 kilopascals. So we'll see kilopascals quite frequently because air pressure is actually pretty high. Back in chemistry, you may have seen the term STP for standard temperature and pressure. In this case, pressure was defined to be exactly 100.0 kilopascals and the temperature to be exactly 0 degrees Celsius. So calculating pressure. Here's an example. I have an 80 kilogram man standing on 1 foot on some ice. Given that his foot is about 8 centimeters by 15 centimeters in cross section, find the pressure on the ice. Well, the force is basically his weight. So mass times gravity, or 80 times 9.8, gives me 784 newtons. The area, making sure I convert to meters, is 0.012 square meters. When I divide that, I find that there's actually quite a lot of force on this ice, 65 kilopascals, as a matter of fact. And that amount of force is actually quite a bit, quite a lot. Hopefully the ice is strong enough so he doesn't fall through. Back when high heels were first coming out, especially the stiletto high heels, Okay, a stiletto high heel is a very, very small surface, and a lot of floor tiles were not designed yet to take that amount of pressure. From a 50-kilogram woman just walking on high heels. So that brings me to Avogadro's number. Okay, Avogadro's number, or the number of count, it's just basically a count of 1 mole of a substance. Okay, normally we only use it for atomic and subatomic particles because the number is really, really large. Okay, the number, Avogadro's number, is 6.02 times 10 to the 23rd. Okay, and when I have that many of some substance, we call that a mole, and the mole is one of the 7 base units that we have in the SI system. The formula little n is equal to big N divided by N sub A is how we convert from moles to actual number. Okay, so 1 mole would have 1 mole of atoms, hydrogen atoms, let's say, would have 6.02 times 10 to the 23rd hydrogen atoms. And occasionally we'll run into atomic weight. The atomic weight of an element is the mass of that element, or the mass of 1 mole of that element, okay, in grams, so be careful. And this is frequently confused with molecular weight, okay, because molecular weight may have a combined weight that is combined mass greater than that. So that brings me to the last slide in this set, which says that temperature and energy are directly correlated. Okay, they're proportional. Okay, temperature directly measures the average kinetic energy of a gas. And I can I have a formula to calculate what that average kinetic energy is based on the temperature of that gas in Kelvin. Okay, so the average kinetic energy is going to be 3/2 Boltzmann constant, which is K sub B, times the temperature in Kelvin. So imagine if my temperature was 0, I would have 0 kinetic energy. Okay, normally my temperature is about 300 degrees Kelvin, and so the average kinetic energy of a single gas molecule is given by 3/2 K sub B times T. Or in another format, it's also 3/2 R, which is the ideal gas constant of 8.31 joules per mole Kelvin. Temperature divided by Avogadro's number, 6.02 times 10 to the 23rd. Okay, so those two formulas are the same. Use either one, that's fine. So this is a bunch of curves at 4 different temperatures, okay? And the reason I have this slide here is I want you to understand that there is a distribution of velocities, okay? The molecular speed has a distribution. The average increases with temperature, and this is what the curves generally look like. Okay, and as I increase the temperature from 100 to 300 to 600 and then 1,000, the kinetic energy, the average kinetic energy does increase. Okay, but the distribution just broadens out. Okay, thank you.